Oh, hey, looks like it's time. Welcome back, everyone. So the new assignment number 8 has been fully posted. It's only going up to section 11.4. And we'll be looking at the further sections 11.5 and 11.6 when we come back from the spring break. So the entire campus is closed next week, but you're always welcome to email or send text anytime, even during spring break. Then we'll have our usual classes these next coming weeks. And our third exam will be right before closed week, a week before closed week, and then we'll have our finals. But any questions so far with where we're at, where we're going?
Are we gonna have like 2 review weeks then, or are we not coming closed week?
Well, we will have our review week on closed week, and that's a good question. Let's see about where we're at so far. Because we did have to make an adjustment on the schedule due to me getting sick. Sorry, your education was expensive. And the adjustment was we lost a day somewhere. Our plan was originally to, when we come back on closed week, cover up to section 10.4. That may not be possible unless we decide not to do 11.11, which is probably what we'll do. Since the chapter 10 is quite important, especially if you're going to Calculus 3, there is a little bit of carryover in what we do versus what they'll be doing in the middle of the course, not the very start. So our goal is we'll have our normal review before exam 3. We'll do a bit of chapter 10, which does go pretty quick. 10.1, for example, is a very, very short section. And depending on where we end off, we'll probably have a day and a half of review before the finals. I don't think we'll dedicate all of Wednesday to 10.4. Other questions about that so far?
You said something about we could replace one of our exams with the final.
Yeah, exactly. So if you had just one exam, which was kind of an off day, it does happen. Then on the finals week, you'll see that there is an extra credit opportunity, where if your final exam is higher than your exam 1, 2, or 3 score, your minimum score from those exams would be replaced by your final exam score. So for example, if you even just got pneumonia and was not able to make exam 1, you wouldn't be necessarily down by whatever 50 divided by 3% comes out to, because your final exam would make it up. Other questions about that?
So the percentage that you get on the final would be comparable to the percentage?
It'd be the exact of the lowest, yeah, correct.
Points would be different, or weight would be different?
The weight is different, correct, but the percent-wise would carry over. So say, for example, my scores were on exams 1, 2, and 3, maybe 98, 97, and I got sick, I got a 32. So if this were my exam 1, 2, and 3 scores, but my final exam was maybe a 91, this is all I'll be doing in the Excel sheet. But then the weights on how grades are calculated in the syllabus are still the usual weights, where exam 1 through 3 is weighted as 55%. Other questions about that? Okay, so we're back to section 11.3, where we got about halfway through it. And before we get too far, looking at new tests and procedures for testing series convergence divergence, I think this is a decent time to just pause, take a deep breath, and analyze all the tests that are on the table so far. So far the tests are, on this, I should space this out a little bit different. The test for divergence, the geometric series test, the p-series test. I put this on the bottom because this is a test of last resort. If nothing else works, there's always the integral test. So let's do a couple review problems where we use those tests. Then we're going to go on to actually estimating sums using the integral test. Any questions then before we start our work for today? Yeah?
So we're reviewing 7.3 before we move into 7.5?
Sort of. We're kind of doing a bit of a review from 7.2 over to 7.3. Then we're going to start 7.4 directly after. Other questions at the moment? Okay, so let's start some problems then. So those are the 4 tests that we've discussed to this point. On exam 2, we only got up to the test for divergence and the geometric series test. And so for the instructions, let's just briefly write test the series for convergence, divergence. So let's just take some random series. The first one is going to be the summation as n goes from 1 to infinity of, let's do 1 divided by n to the power of, let's make it the cube root of n squared. So that'd be the series that we want to consider. It's either going to converge or diverge. If it converges, it will converge to some exact real number. And sometimes we can tell exactly what that is, Other times, we will have to settle for just an estimate of that number. But our major work really is, if we're just given a series, we have to decide what form it takes. For example, is it a p-series, a geometric series, or is it something else? So by analyzing the form of that, what would you say this looks most like? There's really a trichotomy. It's either going to be a p-series, a geometric series, or something else.
P-series?
Turns out it's a p-series, exactly. The thing you want to look for when you're dealing with the p-series is that the index n should be the base. If it was a geometric series, for example, then the index n would have been an exponent instead. So since we know it's a p-series, the work we have to do then is say what the p actually is in the p-series. The nth term is a sub n equals 1 over the cube root of n squared. So let's just simplify this into a better form. If we write this as 1 divided by n, what should the exponent actually be for the nth term? Exactly, or rather it'd be a 2 over 3, like that. Yeah. So we have n to the power of 2/3. That tells us that the p in the p-series test is equal to 2/3. And it's true that this is less than or equal to 1. I mean, it's strictly less than 1, but I like to use less than or equal to 1 because it reminds me of the conclusion of the p-series test. What would our conclusion then be if the power p is 2/3? Right, this causes divergence. But if the power is less than or equal to 1, our conclusion is it diverges. And the reason is by the p-series test. So in a very real sense, this is one of the nicest tests ever, since there's really not a lot of details to get through. There might be some kind of algebra or exponent law that we have to work out to determine the p itself. But aside from that, we just determine if it's less than or equal to 1 for divergence, or if it's greater than 1 for convergence. Any questions about that problem then so far? Okay, when you do these in the homework, there is some extra bullet points on the actual homework assignment. First bullet point says show all necessary steps. I would say these two portions are showing those steps. We worked out algebraically what the power p was, and then we wrote it explicitly as 2/3. Second bullet says clearly state the conclusion of the chosen test, and that's this here. The conclusion is divergence. And the last part was to state which test was used, and that's what we said here. We used the p-series test. Then there's a final bullet about correct notation with summation and limits, but we'll mention those as we go along. Any questions so far with that problem? Okay, so if this was maybe an exam problem out of 6 points, I'd probably break it up as 2 here, and 2 for naming the test. Since really part of the entire problem is to determine what is the series in and of itself and selecting the correct test. And that's the reason for always mentioning the test as well. But questions so far? Yeah.
What if it was conversion? Would another point be finding where it converges at, or?
That's a great question. That's what we're going to do with our estimate of sums. And this is also one kind of unfortunate feature of our tests. Only the geometric series test tells us the exact sum. So on this one, if it did converge, we may not necessarily know what it converges to exactly. It could take quite a lot of math to determine the number it converges to. But what we will be looking at is, later on, the integral test gives us a way to estimate sums. So although I may not be able to tell you if that converged, what it converges to exactly, we can estimate to any amount of precision we'd like. So if you say, I want to find out what the series converges to 20 decimal places, then we would just have to make the index large enough in our estimation S sub n. But we'll get to that at the end of 7 point. Sorry, that's the wrong section. That was the last class. And the section 11.3 in this testing series for convergence divergence. Other questions so far? Okay, so we're in 11.3, we're not in trig, and let's go off to try another one with these tests in mind. Really the struggle with reason chapter 11 is kind of a difficult chapter in some ways, is because this list is going to more than double. So we have to always keep in mind, what does a geometric series look like, what does a p-series look like, and how all the tests work together and interact. Let's go off to a new series. Unless there's any questions or comments first. Okay, so this next one is going to be, let's let it be the summation as n goes from 1 to infinity of n squared divided by the natural logarithm of n. So with same instructions, we want to test for convergence or divergence of this thing. And what would you say this one should be? Geometric, p-series, or something else this time?
Yeah, something else.
Yeah, it's almost a p-series, right? This right here would have made it a p-series, but as soon as you're taking a function of the index, the natural log, now it's the something else. So I cannot use the geometric series test, we cannot use the p-series test. That leaves two tests, test for divergence or the integral test. But keep in mind, I would only use the integral test if I really, really had to. It's the test of last resort, essentially. Test for divergence is a really good thing to look at as a first option. The trouble is, if that does converge, the test for divergence would fail, and we would have to use the integral test if nothing else works. But let's first take a look at the test for divergence and see what happens. So if we take the limit as n goes to infinity of the nth term of the sequence, that would be n squared divided by the natural log of n, we'd be then looking at the limit as n goes to infinity of n squared divided by the natural logarithm of n. So the test tells us if that limit is not 0 or it does not exist, automatically the original series diverges. So we can take this entire problem and really go back to section 11.1, where we're considering whether the sequence converges to something or diverges. Any questions before we work through the limit? Okay, L'Hopital's rule still continues to be a very valuable rule because we have an indeterminate form of type infinity over infinity. So we can start taking the derivative of the numerator by L'Hopital's rule. This becomes a limit as n goes to infinity of up above 2n, the derivative of the natural logarithm of n would be 1 over n. Then if we take the algebraic step on this, 2n divided by 1 over n becomes 2n squared. So this is the limit as n goes to infinity of 2n squared, but 2n squared will get larger and larger as n itself increases larger and larger, so the whole thing goes off to infinity. That means the sequence itself diverges. But remember, that's not the original question. We're concerned about the series. So what would be the conclusion for the series then?
Diverges.
Yeah, so we can say the series, a sub n, as n goes from 1 to infinity, that's referring to this, diverges by, so we have the conclusion, this would be considered all of the work, and the divergence of the conclusion and test for divergence is the name of the test. So that would be the full conclusion on that one. We can, in fact, use the integral test. So there is, on some problems, especially when we're later on in this chapter, more than one way to get a conclusion on this. But the test for divergence, when it works really, really fast. So it's encouraged to always look to see if you can apply that. Any questions about that test so far? Okay, let's maybe try one more, then we'll go on to new things in section 11.3. Let's take a look at, say, n goes from 1 to infinity of the series with nth term a sub n. This is going to be defined as n goes from 1 to infinity of tangent inverse of n divided by n squared plus 1. So that series is definitely not a p-series because, well, if you take the index n and wrap it around a function tangent inverse, it's no longer a p-series at all. Definitely not a geometric series, so we have to try something else. And what would happen on this one is if we took the limit as n goes off to infinity of tangent inverse of n divided by n squared plus 1, this limit is not too bad to do. The numerator tangent inverse at n is bounded by pi over 2. The graph of tangent inverse, if you go off to the right, looks about like this. So we have something that's never going to exceed pi over 2, if the denominator is going to grow larger and larger and larger without bound, so would you say the value of the limit should then be? Should it be 0? Yeah, if we have something that can never exceed a constant, pi divided by 2, the denominator grows without bound, then the limit itself should be 0. What then is our conclusion?
Convergence.
Sadly, it's not convergence. It's horrible. The test for divergence can only give us one conclusion. If we get a limit 0, then what can we say? That was kind of a trick question, sorry. You can't give a real conclusion, but what can we say about the test? What happened with the test itself? Did it work or did it fail?
It had to.
It failed, yes. If we get a limit 0, then we have not met the conclusions. The conclusions on the test for divergence are, in the hypotheses, either the limit was not 0, that's bad because we got the limit of 0, then the series would be divergent. But we did not meet the hypotheses, so the test itself, well, you could say the test failed. That's kind of a mean thing to say. But in truth, we just could never actually apply it in this case. And this is exactly what happens to the harmonic series. The limit is 0, despite the series itself diverging. So sometimes the test for divergence is really great. Other times when you get a limit 0 in the test for divergence, that's terrible because now we have to pick a new test. So what test is left then? The integral test. So we just have to use that test as our last option. And again, that's a test of last resort, so we're going to use it here. But to finish off the comment on this, the test for divergence failed is typically what people would say. And what we mean by that is no conclusion can be drawn from this. So we do something else. So we're going to hit this entire series with one of the most powerful tests we have, the integral test. To do that, we have to come up with a function. We start by letting f of x be equal to the continuous analog of this sequence. So we'll make a continuous version of the sequence. We just take tangent inverse of x divided by x squared plus 1. So that'll be our function. And if you're doing these problems in the homework, one thing you'll notice in section 11.3 specifically, many of the problems just say, use the integral test to test for convergence divergence. If that's the case, you don't necessarily have to check the conditions. But if you're in sections 11.4 through 11.10, and the integral test comes up, you should check the conditions in those settings. Let's just mention the conditions anyways. The first thing is that f of x is continuous outright. No matter what number we put on there, there's not a single point of discontinuity. That's because tangent inverse is continuous, n squared plus 1 is continuous and never 0. So the entire fraction that we see there is continuous on the entire real number line. So that's one bullet down. What's the next thing that we have to check in order to use the integral test? You need continuity and then right, we have to have a positive function. This is actually a bit of a conflict because we're going to accrue a lot of tests that specifically force the terms or the function that we define to be positive. But f of x is positive on the domain from 1 to infinity. There's not much to say about this. You just have to assert that this is the case. If it's not the case, then we made a mistake and can't use the test. But the reason that that function is positive is, once again, the numerator looks about like this, where if we are beyond 0, the curve is always above the x-axis. Then down below, x squared plus 1 is always a positive function itself. So we have a ratio of positive functions on that domain. So it's positive, and we're still in good shape. What's the last condition then? It has to be continuous, positive, and
Isn't it decreasing?
decreasing, correct. So f of x is decreasing. All right, DEC is short for decreasing. Once again, you can possibly use a lot of algebra to show this. We did do the first derivative test to show something is increasing or decreasing. And you may want to do that when you look on the last problem, 27 and 11.3, where they'll give you a series and ask you, why can you not use the integral test? One of these three things have failed. After you take the derivative and find it's ever positive, that would mean it's increasing, which violates this. But this curve is decreasing because tangent inverse n, although it does increase, it's being dampened out by n squared plus 1. So the value gets smaller and smaller and smaller as n or x increases ever larger. But it's not much of a proof unless we do something else. So I'll leave it to folks. Should we investigate that further with the first derivative test, or just move on to the next step? Your choice today.
Can we do the extra?
Let's do it. So let's take and prove that f of x is really decreasing. To do that, we need to take the derivative of f of x. So we're probably going to need a lot more space. So f of x prime, by the quotient rule, is going to look about like this. So the denominator is always the denominator of the original function squared. So we'll throw that in. Notice that we're just trying to determine the sign of the derivative, f prime. And it's nice to know the denominator is now always positive, no matter what. So whether this thing becomes positive or negative depends on what goes here. We're hoping for a larger quantity to this side of that negative sign. So depending on the pattern you do it, I would typically take the derivative of this, that has to be on the left of the negative sign. So derivative of tangent inverse of x is 1 over 1 plus x squared, and it has to multiply the denominator, x squared plus 1. So there's a nice cancellation right there immediately. Then, for the next portion, we copy tangent inverse of x, and we multiply by the derivative of 2x plus 1. So times 2x, or just 2x, would be the derivative of x squared plus 1. So there it all is. And if we simplify the numerator, this turns into 1 minus twice x times tangent inverse of x divided by x squared plus 1 squared. So as it stands, as soon as this quantity is larger than 1, the entire numerator is going to be negative, and that means the first derivative, f prime of x, is less than 0 whenever 1 minus 2x tangent inverse x is less than 0. But thanks to that 2x there, if we put in just 1 itself, tangent inverse of 1 is pi divided by 4. Pi divided by 4 times negative 2x. That looks like, yeah, let's take a look at that. So if x equals 1, I'm inserting it into this left-hand side, we will get 1 minus 2 tangent inverse at 1. But tangent inverse 1 is pi over 4, so this turns into 1 minus 2 times pi over 4, which is 1 minus pi divided by 2. But if we use the crude approximation that pi is 3, that's really horrible, that's going to be terrible work if you do that in carpentry. This is about equal to 1 minus 1.5, which is negative. So that's some good numerical evidence that this thing is always negative if we're starting at 1 and going off to infinity. If we plug in the value 2, it's just going to become more negative because tangent inverse is increasing. So we can say that this is true whenever that's less than 0, which is whenever x is bigger than or equal to 1. So that proves the decreasing portion. So if we need a big tool to get decreasing, usually the first derivative is the most straightforward way to do it, whereas doing this algebraically can be very, very finicky. Other questions so far? Okay, so far we're ready to start the test. We found out we can use the integral test. Now we have to actually do it. And this is the downside of the integral test. Even if we're taking the hypotheses as granted, because the problems in the book says use the integral test, that test must apply, it's still a long test because we have to solve an improper integral. So let's do that next over here. We're going to look at the improper integral as the domain for x varies from 1 to infinity of f of x dx, where f of x is tangent inverse divided by x squared plus 1. So this can be converted into the limit as t goes to infinity of the definite integral from 1 to t of f of x is tangent inverse of x divided by x squared plus 1 dx. So now we need to find and solve the antiderivative for tangent inverse x divided by x squared plus 1 as our very next step. But any questions so far with this problem? Okay, so what would you say the approach should be to solve antiderivative tangent inverse at x divided by x squared plus 1? I would say integration by parts is definitely out. Would you folks agree? You usually want two quantities in the numerator to make that happen. And the algebra to make x squared plus 1 emerge in the numerator is not going to make by parts work so very well. So what would you say is the next option if integration by parts is out? U substitution ought to work. Yeah, so if we let u be something, then we can just hope for the best. And if I let u be x squared plus 1, there's just no chance, right? Du would then be 2x dx, and that doesn't match anything in the problem. So let's just go for something else. Let's let u be tangent inverse of x. Then we go to the differential equation. What would be the derivative of tangent inverse at x?
1 over x squared plus 1.
Exactly, yes, which is nice because that's precisely what we have down below. So the derivative of tangent inverse x, 1 over 1 plus x squared, as you said, then in dx. So we do have that. I mean, the order is different, but it's there. All of this is du. So the u substitution would be successful. That means we can now go to the next step and say now we're dealing with the limit as t goes to infinity of the definite integral, and we have to decide if we want to change the limits now or later. The work is the same either way you do it. Maybe let's do it later for those folks that prefer to do it that way. We typically do it right at this step. I'll leave it as x goes from 1 to t, just to remind me this is the variable x, and I have to undo a substitution. We let u be tangent inverse, and du was 1 over x squared plus 1. So that's the new integral. We now need the antiderivative of u. That's kind of nice. Questions so far to that step? Okay, so antiderivative of u, still we need the limit as t goes to infinity, and antiderivative of u is u squared divided by 2, evaluated as x goes from 1 to t, which means we have to, as the very next step, undo this substitution. So this is then, let's take a half and bring it in front of the limit as t goes to infinity of tangent inverse of x quantity squared as we evaluate from 1 to t. So this is what undoing the substitution would look like to that step. Does that look all right to folks so far? Okay, so now let's evaluate from 1 to t. This becomes 1/2 limit as t goes to infinity of, we have lots of brackets going on here. I'll go tangent inverse of t quantity squared minus tangent inverse at 1 squared. So that's our limit to take. Then once again, we need the graph of tangent inverse. As the variable goes off to infinity, t, we would be approaching pi over 2. So we just use the fact that tangent inverse has a known horizontal asymptote, and the definition of the limit at infinity being constant means the value would be that asymptote. So we have now, upon evaluation, 1/2 times, this is going to be tangent inverse at t, as t goes to infinity, a pi over 2 squared, minus tangent inverse at 1 is pi over 4, and that quantity is squared with a bracket. So that's where the limit would end, where all we've done is said that this tangent inverse converges to, pi over 2 as t goes off to infinity. Then this would be something we could simplify and work out a little bit more. But remember, our sole goal to this stage is to say that this integral, what does it do? It would converge, just because we got to some real number. It's not infinity, does not exist. that means the original integral converges. Okay, so far we've done a couple things. First thing we've done is we showed all necessary steps of the chosen test, we verified the hypotheses, and we worked out the definite integral. So all of that work is just this single bullet. We haven't really stated the conclusion so far. This is just saying the improper integral itself converges. So our conclusion is then the original series as n goes from 1 to infinity of a sub n, would that converge or diverge by the integral test?
Converges.
Yes, if the improper integral converges, so does the original series way over there. So this converges. And that's stating the conclusion that was used. Or yes, we clearly stated the conclusion. The series must then converge. And we just say by what test? Let's just throw in there by the, if you like, INT is a decent shorthand for integral test. That's a really long problem. Really half of the work, well, yeah, probably half of the work was just verifying the hypotheses of that chosen test, where we also proved very rigorously that that function was indeed decreasing. Any questions about that test? It's not the most exciting test because it requires a lot of hypothesis checking and a lot of details to work out. So my advice is, if you're testing for series convergence divergence, and you're in a section beyond 11.3 where any test is on the table, I would always consider this last. Definitely at least eyeball it and see if the test for divergence may possibly work, because that is always faster when it does. But any questions so far with what we've done in 11.3? Okay, so what we've shown so far is that this, in fact, converges. But a question already asked today, which is a very common question, is the following. This, as n goes from 1 to infinity, of tangent inverse of n divided by n squared plus 1, converges to what? Real number. This is something that we were able to say precisely with just the geometric series test. If we have convergence on the geometric series test, it converges to the total sum, a divided by 1 minus r, the common ratio. However, for every other test, I mean for test for divergence, there is no convergence to say what it converges to. Then for the p-series test and the integral test, there's no conclusion on what we actually converge to. And that's sadly pretty typical. However, if we really need to say what happens when you take things like this and add them infinitely many terms together, we can estimate it at least. So that's what we're going to do next. Any questions first before we estimate sums? Okay, the formulas we're going to give for the estimate are really nice in that we can, if we'd like, get any decimal point accuracy precision we would want to this. So if someone wants 10 points of precision, an answer accurate to 10 decimal points, then we can figure out what the correct index n would be to make that happen. We can even do a little bit better in that if we ever make an estimate, we can put a bounds on how much of the error we have, or the remainder. So let's write out next what the formulas are for those things. This gives us a decent opportunity to, once again, catch our breath and review all the moving parts so far and how we're going to estimate our series. So we'll start with a big old definition. This was a portion of the, I think, next to the last problem on exam 2, where we are going to do the following. We'll say let a sub n, as n goes from 1 to infinity, be a sequence with associated sequence of partial sums. This sequence, S sub n, as n goes from 1 to infinity. So if we give any sequence whatsoever, then there's a sequence S sub n, where S sub n is defined to be a1 plus a2 plus the nth term. So there's this finitely many terms, and altogether that we're adding together in S sub n. When we look at a series, we're trying to add infinitely many terms. So this is a stepping stone in that direction. The next thing we want to say is, assume that the series, the summation as n goes from 1 to infinity of a sub n converges. Just like in our very last problem. If the series converges, then what we can say is, then the summation as n goes from 1 to infinity of a sub n would be equal to the limit as n goes to infinity of S sub n. So S sub n can converge or diverge, but if we said that the series converges, then this would converge to some real number. Sometimes we call it lowercase s. So that would be our total sum. Really, the battle is if you can get a formula for the total sum, and you did that, say, in the last problem that we just worked, you could tell us exactly what it converges to. But in practice, getting a formula for the partial sums, S sub n, is really, really hard. It's just a fluke, an accident in algebra, that we could do it for the geometric series test. But still, if we want to estimate this thing, which has infinitely many terms, we just don't let this go to infinity. We just let n be large. So we can estimate the summation as n goes from 1 to infinity of a sub n, which is equal to a1 plus a2 plus a3. There's infinitely many terms. We eventually reach a sub n, and then a sub n plus 1, a sub n plus 2, and so on forever. So we can estimate that thing. This is just two ways to write the same series by using S sub n, which is equal to a1 plus a2, all the way to a sub n. So in other words, if we want a decent approximation to any series whatsoever, provided it converges, that's the important bit, we just cut it off short to the partial sum S sub n. So the partial sums themselves are approximations to a convergent series. Does that make sense so far about that? Okay, so in the very last problem, if you calculated S sub 10, then that would be an approximation. There's a problem with that. My question would then be, well, you've approximated the last series that converges with S sub 10. I might come in and say, well, how good was the approximation actually? And that's something we can do further in the integral test. For other tests, you need different methods. For example, the p-series test was proved using the integral test, so we can use our estimations that we're going to give. But later down the line with the comparison tests that we're going to get into, there is no good formula for the remainder. But however, if we look at these terms, we sometimes think of this as the error, or remainder R sub n. So this is the remainder, or sometimes thought of it as the error, upon estimating the entire total sum of the series with a partial sum. So that's our goal, is to now estimate, and also say how good the estimate was, by also estimating the remainder itself. Does that make sense what the approach then is? Okay, so I want to approximate a convergent series by taking S sub n, and then say, how big could this possibly be, to also give some measure of accuracy in the approximation we made. Because if we estimate something and we can't say how accurate the estimate was, really the estimate is good for nothing. Would you folks agree with that sentiment? So we have to say how much precision we have in the estimate, and specifically in the case of the integral test, this can be done. This is the second half of 11.3. We're not going to emphasize it a terrible amount, but still an important problem. And this is the remainder estimate for the integral test. So if your problem can be shown to be convergent by using the integral test, and that includes all of p-series, then the remainder R sub n can be estimated as the upper bound. This is the worst case error. Integrate from n to infinity of f of x. The best case error, the smallest the error could ever be, is integrate from n plus 1 to infinity of f of x dx. That seems kind of strange, but the graphs down here are meant to show how that really should work. If, for example, the remainder is an plus 1, an plus 2, like we said over there, then these boxes would indicate the summation from an plus 1, an plus 2 off to infinity forever. And if we integrate from n all the way to infinity for f of x, this portion here, then that would be an overestimate on the error due to the way the geometry works out for each of these rectangles. Does that make sense for the overestimate, the upper estimate here? Okay, then at the same token, if you want a lower estimate, this is what the graph would be. So if we looked at an plus 1, an plus 2, and we start integrating n plus 1, then this integration is going to be an underestimate by the way these rectangles are arranged. And so in that case, we come up with this overall bound for r sub n. We can either find the greatest the error could possibly be, or the worst or the best the error, the smallest it could ever possibly be, or just get both results as a measure of how confident we are in our estimating. So let's do that very next. Unless there's any questions about that test. Okay, well, the remainder estimate rather. So the remainder estimate says, suppose that f of n equals a sub n, where f is continuous positive decreasing for x bigger than or equal to n, then this has to be convergent. And if that's the case, we can estimate the remainder in this way. But really what that test is saying is, if you have a series that is convergent by the integral test, then we can estimate the remainder upon using an nth partial sum by that formula. So let's walk through all that with a particular example. We're going to take a p-series just to make the process a little bit more friendly and focus on it rather than all of the algebra like in the last problem. And this is what the instructions may look like. It says to estimate the sum of the series, summation as n goes from 1 to infinity of 1 divided by n to the power 4 using the first 5 terms. Then, for the second portion, we want to do the following. We want to say, then determine how accurate this estimate is. So we're ready to start. First thing we should do is we should check that we can actually use this estimation theorem. Since this theorem can only be used specifically when you have convergence by the integral test. But what I would say for this particular problem is that summation as n goes from 1 to infinity of 1 over n to the power 4 is a convergent p-series with p is equal to 4, which is bigger than 1, giving the convergence. Then we know, well, we mentioned it a little bit, we only proved 1/3 of the entire theorem. The p-series test is proven using the integral test. So if I have convergence by the p-series test, automatically we would have convergence by the integral test itself, which means we can use that specific estimate for the remainder r sub n. So I'll add that next. Then we may use the integral test how do we say that? The integral, well, the remainder for the integral test. That's probably the more grammatical way to say it. We may use the remainder estimate for the integral test since this is a p-series. So in the special case of a p-series, you don't actually have to run through the integral test. You're okay to skip to this step. So first thing we want to do is actually estimate 1 over n to the power 4 as we sum those terms from n goes from 1 to infinity. So saying estimate it using the first 5 terms means we're really just doing this estimate. It should be approximately equal to S sub 5. Now we just have to write out what the formula for S sub 5 is and evaluate. Does that make sense so far? Okay, so our series, this one, which converges, really looks like this if we use the expanded notation. And estimating S sub 5 means there is a remainder that we should estimate to determine how good the estimate really was. But first, we're going to do this portion and actually estimate. So S sub 5 is equal to A1 plus A2 plus A3 plus A4 up to A5, where this is the nth term, A sub n. So A sub n is 1 over n to the power 4, and we can evaluate that to say at 1, we just get 1, plus at 2, it's 1 over 2 to the power 4. At 3, it's 1 over 3 to the power 4, and so on, until we get 1 over 5 to the power 4. So plus 1 over 4 to the power 4 plus 1 over 5 to the power 4. Then if this was an exam problem, you can just leave it like that, exactly in that form. But if you're curious on doing a homework problem, it's always good to estimate this to see if we're on the right track. So this altogether comes out, when you drop everything into the calculator, to about 1.08035. Provided I did all those keystrokes perfectly, that's what the estimate would be. So 1 over n to the power 4 is about 1.08 and some change. Any questions about that? Okay, then the second portion, what we're going to try to do is say, well, we only used 5 terms. There's supposedly infinitely many terms we're adding. That's the R sub n portion and so on. So we also have to say, how good is this estimate if we make any estimate of this kind? Depending on the form of the series, this could be a really horrible estimate if this converges slowly. But with a power 4, things are getting closer and closer to 0 really fast on the terms of the sequence. So it may be a fantastic estimate, in fact. So we'll find out by using that theorem up above. So now we're going to determine how accurate this estimate is. So we'll say R sub n equals an plus 1 plus an plus 2, so on. This has infinitely many terms, and it can be estimated by typically I look at this integral first. If we take the definite integral as we go from n to infinity of f of x dx, then we're looking at the upper bound of that estimate. We're trying to find how big could the remainder ever be, and then in some sense we're trying to find the maximal error to this estimate. So I think that's a good one to look at first. And if it was an exam problem, I'd probably ask you to just do the upper bound of the estimate, so that we don't have to do 2 integrals at once for a single problem. It's best to see how bad things can be first. So let's work that out. What would you say the n should be then in this problem? It really would come from way over here. If we estimate using S sub n, then we get a particular n that we're going to work with. So what was S sub n actually?
It's 5, right?
Yeah, so we estimated using S sub 5. That means the n itself is going to be 5 down below. So we're going from 5 to infinity. Next portion is, what would you say the f of x should be?
It's the same thing, right? Same formula, 1 over n to the 4.
Exactly, yes. We were going to use instead a 1 over x to the power 4, but really that's the exact same thing. It's just a matter of change of variables. If you went 1 over n to the power 4, you would just have a dn here and be completely consistent. X is really just a dummy variable. We're using f of x just to remind us that we did take the sequence, which is a discrete set of points, we made it continuous so we can actually integrate something. That's what's producing this curve over here, whereas the sequence would just be the points here, here, and here, and so on. So we use x to remind us that this can be done by taking the continuous function, converting to the limit as x now, or t rather, goes to infinity, of the definite integral from 5 to t, I'd call it x to the power negative 4 dx. So it's really not a terrible integral. Really the organization of what to do and when to do it is the big portion of this, because there's lots of definitions working at once, and now a huge theorem at the same time. But if we get through the limit, we can start with the antiderivative and say this is the limit as t goes to infinity of the power would go up by 1, so negative 3, and we have to divide by that new power. So we have negative 1/3, which you can throw way in front of the limit if you prefer. This is evaluated from 5 to t. Any questions so far? Okay, so if we evaluate this, we get negative 1/3, the limit as t goes off to infinity of, this evaluated at t would be 1 over t cubed, minus evaluated at 5 would be 1 over 5 cubed, and the limit 1 over t squared as t goes to infinity, or excuse me, cubed as t goes into infinity, converges to 0. So this is negative 1/3 times negative 1 over 5 to the power thirds, which is positive 1 over, that's something like 5 cubed is 125, so it's 375. So the estimate we gave of 1.08035 is no worse than off by 1/375th in either direction. It could have been an over or an underestimate, but that is the worst case. So it really isn't too shabby, and depending on what we're actually doing with that series, if we go up to 10, we can find that it's even more accurate by quite a lot. Any questions about that so far?
So
Yeah.
what would be a bad estimate? Like, what would be an approximation that would be a bad estimate?
That's a good question. It kind of depends on context as well, but something that converges slowly using just 5 terms could potentially be a bad estimate. And again, it just depends on what you're trying to achieve with this. If we're trying to do some rigorous maritime engineering, 1/375ths might be horrible. Maybe all of our oil tankers are going to sink if we do that. So the context is really important. And also if we look at things like, say, take a geometric series and make it be something like this, maybe 99999 divided by 10000, so I want 3 zeros, 4, 5. Let's go with 6 zeros. So if I look at something like this, it just barely meets the conditions of convergence by the geometric series test. If that's the case, we're probably going to want to do something like S sub 20 as a good estimate for that one. So how many terms you need for a good estimate or bad estimate is dependent on how fast things are converging. So say, for example, if we converted this to n squared, it still converges, but we're going to find this value does change, but the remainder is going to be much bigger because we don't have the terms getting smaller and smaller in the same rate that they were with this series. Other questions about that, though? Okay, so I feel like the upper limit of the estimation is typically what people are mostly interested in. So when you're doing this in homework, I'll leave it up to you folks. If you just give me the upper limit of estimate, then that would be just fine on this. The lower limit of estimate is something that's interesting as well. It tells us how good the estimate could possibly be. If people are interested, we could compute that as well. Should we do that second one just for the sake of completion? Okay, let's do it then. So this is, in some sense, the worst case. We're off by 1/375th, but we cannot be any worse than this. So now we're going to come up with the best case, and we'll find that our estimate could not possibly be any better than that estimate. That still could be something interesting to know. We can say that the lower bound of the estimate remainder is the definite integral from n plus 1 to infinity of f of x dx. We said in both cases we're using n is 5 because of the first 5 terms in the estimate. So we would be doing the definite integral from 6 to infinity, this time, of 1 over x to the power of 4 dx. But one thing to note is that if you've done this once, all this work is exactly the same, except for that. So let's treat ourselves to a massive shortcut because we've done it once. We don't have to do it several times. It's still negative 1/3 times the limit as t goes to infinity of, it'll still be 1 over t cubed, but this time it's 1 over, not 5, which came from here, which came from the first 5 terms, but it would be 6 cubed. It's smaller, but that's because we're getting the best case estimate this time. So this would become altogether positive 1 over 3 times 6 cubed, whatever that turns out to be. Any questions with that one? Okay, so that's the best the remainder could possibly be. So if we take this quantity, add it and subtract it to this, that would be the best case for the error in estimating that quantity. But again, this is probably the better value because we typically want to say how bad the estimate could be. We want to have the worst cases when we do these kinds of work. But that's estimating sums. Any questions at all about these kinds of problems? Okay, there won't be a lot of these in the actual homework. The main work is going to be the integral test itself in this homework set. But it is interesting to know that even if we use the integral test, I cannot tell you what our series converges to exactly. I do not know what 1 over n to the power 4 converges to. But with any desired level of accuracy, we can just do an estimate with, say, 20 terms. We'll find that the decimal points are starting to stabilize very, very quickly as the number of terms increase. So we can very rapidly give very decent approximations in some cases. Let's go off to section 11.4 then, which will finish on Thursday. Any questions first before we go on to new and greater territory?
Were there any estimate problems on the homework review 11.3?
I was just thinking about that. I don't think I did actually assign one. I think the last problem was determine when or when the integral test cannot be used.
27.
Yeah, I believe 27 was the last one on that. So this is kind of just bonus material, possibly. Other questions about that so far? Okay, let's go off then to 11.4 next. This chalk was cheaper than I realized. It does not want to erase very well. I have to use it very, very sparingly. .4 is the so-called comparison tests. So there's 2 tests altogether that we're going to look at. The first test is called just the comparison test. So let's state that test first. The comparison test. For both the comparison test and the limit comparison test very next, there's 2 sequences we have to look at very, very carefully. So first we'll start off by saying, let a sub n, as n goes from 1 to infinity, and b sub n, as n goes from 1 to infinity, be 2 sequences with positive terms. This is a bit of a restriction, but if you had a sequence with all negative terms, you can multiply that sequence by -1 and see if it converges or diverges. Since a constant multiple of a series is not really going to affect convergence divergence. But if you have terms that are alternating positive, negative, such that things with cosine and sine, then none of these tests could work at all. Not the integral test, nor the comparison test, nor the limit comparison test. So we do have a bit of a dilemma with the test that we're building. But we'll see how to get around that soon. So we have 2 sequences. Typically, this is going to produce a series we're trying to test for convergence divergence. And we can compare it to something that's known to converge or diverge. And this is what the conclusions would look like. For the first conclusion, we say if a sub n is less than or equal to b sub n, this is the main bit, and this is just for emphasis. We said the terms were positive, so a sub n has to be bigger than 0 itself. And if this holds for all n, and if the series with b sub n, as n goes from 1 to infinity, converges, then the series, as n goes from 1 to infinity of a sub n, must also converge. And the logic behind that is, if we have this sequence such that b sub n is always larger than every single term in the other sequence, then if the terms get smaller and smaller fast enough so that this converges, then this has no choice but to converge as well, because all the terms are smaller than a known convergent sequence. So that's the logic of the first portion. Does that seem like it's believable? That should be the case? Awesome, we'll skip the proof. Then let's go to the second case. Case 2 is that if we have the opposite situation, that b sub n is, we could put less than or equals to here. We don't have to be super punishing. If b sub n is less than or equal to a sub n, and if the series, as n goes from 1 to infinity, of b sub n, what would you say should be in this case? Should we say converges or diverges? A sub n is now larger than b sub n. Yeah, we want to go for diverges this time. We're going to say all the terms of one series is larger than all the terms of the other one, where this one diverges. Then, the series, as n goes from 1 to infinity, of a sub n must also diverge. And the logic is, we just said all of the terms are larger in this series compared to a series that's already divergent. So if we make the terms larger than an already divergent series, we must still be diverging. There's no rescuing it any longer. So that's the entire comparison test. Any questions about it so far? Okay, when the comparison test works, it is really, really fast. So we kind of like this test as opposed to that integral test and estimation of sums. So let's do a couple problems where this test works wonderfully. Then we'll look at reasons why we need a limit comparison test. Because when the test doesn't work, it really, really doesn't work. It becomes a big problem. So here, once again, we're going to test for convergence, divergence, with full guidance on how the points are scored up on Moodle still. And let's do, say, this thing. Summation, as n goes from 1 to infinity, of a sub n is going to be the summation as n goes from 1 to infinity of n minus 1 in the numerator divided by n cubed plus 1 in the denominator. So that's the thing we want to test for, convergence or divergence. And what we could do is, well, it's not a geometric series, so we could go down the list of tests. The limit of this thing as n goes to infinity is 0, so test for divergence is out. And it's almost a p-series. If that's all we had, that's a bona fide p-series with p equals 2. But these things make it not a p-series. We cannot actually use the p-series test on this. So we could use the integral test, but then you'd have to solve this as an antiderivative. And that could be a very substantial amount of work. It may not be too bad, but it's lots of stuff to work through. So instead, we're going to use the comparison test. I want to take the terms a sub n, see if I can estimate it with something like b sub n, either this way or this way. But first we have to decide, if you look at this, does that look like it converges or does it look like it diverges?
Converges.
I would agree with that, because if we looked at just this much, that would be a p-series with p equals 2, which is convergent. So that's what I'm trying to compare it to, a known convergent p-series. So that kind of guides us our work. We're trying to show this kind of inequality. We'll take our a sub n, which is by formula n minus 1 divided by n cubed plus 1. And this is what we're going to start trying to do. Try to make it less. And if our estimate calls for it, we may have to use less than or equals to. But the first thing I would do to try to make it less than something is, well, how about we increase this by 1? If I make the numerator bigger by 1, then this would be smaller immediately. Do you folks agree with that so far? Okay, then it's still not a p-series if this is the nth term, so we have to do something with the denominator. But in the denominator, we have n cubed plus 1. If we go to just n cubed, that's what I want. The constants are what's ruining everything. I would say that this is greater than in this direction. Now if we take the reciprocal of both sides, 1 over n cubed plus 1 is less than 1 over n cubed. When we take the reciprocal of both sides, the directionality has to also change. And the logic is, this is altogether smaller, and if I divide 1 by something smaller over here, I would have something that is, or hang on, 1 over n cubed plus 1 is bigger than n cubed. And if I divide by something that's bigger into 1, I get something that's smaller altogether. Does that make sense so far? It's a lot of directionality with the inequality signs. So you could also, if you like, just divide both sides by n cubed, divide both sides by n cubed plus 1, and it produces that immediately. But as an algebraic step, in an inequality, reciprocals of both sides always give you a reversal in that direction. So that means if we go over here to n, divide by n cubed, this should still be a less than. And this is the trouble with the comparison test. If that was a minus 1, and I went to n cubed, it would have been a greater than, and the whole test is ruined. We'd have to try to estimate in a different way, or more likely, just use a different test, the limit comparison test. But next, let's simplify this. This is 1 over n squared altogether. And we're going to call that b sub n in this formula so far. So far, we have a sequence which involves terms that are always going to be not negative. When n is 1, we do get 0, but that being positive would hold from 2 and beyond. We also know that a sub n is always less than or equal to b sub n, which is 1 over n squared. So the second portion of this test that we're trying to use is we have to take a look at this. Consider the summation as n goes from 1 to infinity of b sub n, which is the summation as n goes from 1 to infinity of 1 over n squared. We do have to test this for convergence divergence, but oftentimes that is really quick. We can say that this is a convergent p-series with p is equal to 2. So the thing we compare it to, the b sub n series, it does have to be tested for convergence and divergence as well, so that we can meet that portion of the hypotheses. But that means we're ready for the conclusion. We can say, then, the series as n goes from 1 to infinity of a sub n, already indicated to be the n minus 1 divided by n cubed plus 1 for the nth term, does it converge or diverge? It must converge. And this is by the comparison test. So that concludes the test for this particular series. One thing to take away from this is that when we do the comparison test and the limit comparison test, we are starting to stitch together all of the other tests at the same time. That is concerning, and that's part of the reason why it starts to become really, really helpful to have a list of all the series we have up to date and study them extensively, because pattern recognition and determining which is the correct test to put together becomes really the whole battle with this kind of stuff. But we'll get there, and on Thursday we'll look at more examples with the comparison test and also the limit comparison test as well. But if you have questions, feel free to stick around. I'm happy to help.